Download this code from codegive.com, link in the description below. OK, let's dive into the world of neural networks. This will be a comprehensive tutorial covering the fundamental concepts, building blocks, common architectures, training algorithms, and practical code examples using Python and TensorFlow/keras. Introduction. What are neural networks? Neural networks are a subset of machine learning, inspired by the structure and function of the human brain. They're designed to recognize patterns, learn from data, and make predictions. Essentially, they're a collection of interconnected nodes, neurons, organized in layers that process information and pass it along to subsequent layers. Key idea mimic the way biological neurons communicate to learn complex relationships in data. Power neural networks can approximate virtually any continuous function, making them powerful for tasks like image recognition, natural language processing, time series forecasting, and more. Complexity while the underlying concepts are relatively simple, designing, training, and tuning neural networks can be challenging due to the vast number of parameters and the need for careful data preparation. 2. Core components of a neural network. 1. Neurons, nodes. The fundamental processing unit of a neural network. Receives inputs, performs a calculation, and produces an output. The calculation involves a weighted sum of the inputs plus a bias, followed by an activation function. 2. Weights represent the strength of the connection between neurons. Larger weights indicate a stronger influence of the corresponding input on the neuron's output. Weights are adjusted during training to improve the network's accuracy. 3. Bias a constant value added to the weighted sum of inputs. Allows the neuron to activate even when all inputs are 0. Similar to an intercept in a linear equation. 4. Activation functions introduce nonlinearity into the network. Without nonlinear activation functions, the entire neural network would simply be a linear regression model, severely limiting its ability to learn complex patterns. Common activation functions. Sigmoid sigma, x, equals 1/1 plus exp, x. Output between 0 and 1. Historically popular but can suffer from vanishing gradients. ReLU, rectified linear unit ReLU, x, equals max, 0, x. Simple and widely used. Can suffer from dying ReLU problem. 10, hyperbolic tangent 10, x, equals, exp, x, exp, x, slash, exp, x, plus exp, x. Output between -1 and 1. Softmax used in the output layer for multi-class classification. Normalizes the outputs into a probability distribution. 5 layers neurons are organized into layers. Input layer receives the initial data. The number of neurons in this layer corresponds to the number of features in your data set. Hidden layers layers between the input and output layers. These layers perform the complex transformations of the input data. A network can have multiple hidden layers, deep learning. Output layer produces the final prediction. The number of neurons in this layer depends on the task, example 1 neuron for binary classification, multiple neurons for multi-class classification. 3. Neural network architectures. 1. Feed-forward neural networks, FFNNs. The simplest type of neural network. Information flows in one direction, from the input layer to the output layer, through the hidden layers. Asterisk no loops or cycles. Asterisk suitable for many classification and regression tasks. 2 convolutional neural networks, CNNs. Asterisk specifically designed for processing data with a grid-like structure, such as images. Asterisk use convolutional layers to automatically learn spatial hierarchies of features. Asterisk key components. Asterisk convolutional layers. Asterisk apply filters, kernels, to extract features from the input. Asterisk pooling layers. Asterisk reduce the spatial dimensions of the feature maps, reducing the number of parameters and making the network more robust to variations in the input. Asterisk fully connected layers. Asterisk used to combine the features extracted by the convolutional and pooling layers to make a final prediction. See tensorflow/keras example later. 3 recurrent neural networks, RNNs. Asterisk designed for processing sequential data, such as text or time series. Asterisk have recurrent connections, allowing them to maintain a memory of previous inputs. Asterisk key types. Asterisk simple RNNs. Asterisk basic recurrent architecture but suffer from vanishing/exploding gradients. Asterisk LSTMs, long short-term memory. More sophisticated recurrent architecture with memory cells and gates that control the flow of information. Handles long-term dependencies better than simple RNNs. Asterisk GRUs, gated recurrent units. Simplified version of LSTMs with fewer parameters. See tensorflow/keras example later. 4 other architectures. Asterisk transformers. Asterisk attention-based models that have revolutionized natural language processing. BERT, GPT, etc. Asterisk generative adversarial networks, GANs used for generating new data that resembles the training data. Asterisk autoencoders. Asterisk used for dimensionality reduction and feature learning. 4. Training a neural network. 1 loss function. Asterisk measures the difference between the network's predictions and the actual target values. The goal of training is to minimize the loss function. Common loss functions. Mean squared error, MSE used for regression tasks. Binary cross entropy. Used for binary classification. Categorical cross entropy. Used for multi-class classification. 2 optimization algorithm. An algorithm that adjusts the weights and biases of the network to minimize the loss function. Gradient descent. The most basic optimization algorithm. It iteratively updates the parameters in the direction of the negative gradient of the loss function. Stochastic gradient descent, SGD. A variant of gradient descent that updates the parameters based on a single training example or a small batch of examples. ATOM. A popular adaptive optimization algorithm that combines the benefits of momentum and RMS-prop. 3 backpropagation. An algorithm that efficiently calculates the gradient of the loss function with respect to the weights and biases of the network. Uses the chain rule of calculus to propagate the error signal backward through the network. 4 training process. Forward pass. Input data is fed through the network to generate a prediction. Loss calculation. The loss function is calculated to measure the error between the prediction and the target value. Backpropagation. The gradient of the loss function is calculated using backpropagation. Parameter update. The weights and biases are updated using the optimization algorithm. Repeat steps 1 to 4 for multiple epochs, iterations over the entire training dataset. 5 regularization. Techniques used to prevent overfitting, when the network learns the training data too well and performs poorly on unseen data. Asterisk common regularization techniques. Asterisk L1 and L2 regularization. Asterisk add a penalty term to the loss function based on the magnitude of the weights. Asterisk dropout. Asterisk randomly drops out neurons during training, forcing the network to learn more robust features. Asterisk early stopping. Asterisk monitor the performance of the network on a validation set and stop training when the performance starts to degrade. V TensorFlow/keras code examples. TensorFlow and keras are popular libraries for building and training neural networks. Keras provides a high-level API that makes it easy to define and train models, while TensorFlow provides a more flexible and powerful low-level API. One simple feed-forward network with keras. Asterisk 2 convolutional neural network, CNN, for image classification, NIST dataset. 3 recurrent neural network, RNN, for text classification, IMDb dataset. 6. Important considerations and tips. Asterisk data preprocessing. Asterisk neural networks are highly sensitive to the quality and format of the input data. Proper preprocessing is crucial for good performance. This includes asterisk normalization/standardization, asterisk scaling the data to have a mean of 0 and a standard deviation of 1, or scaling the data to a range between 0 and 1. Asterisk handling missing values, asterisk imputing missing values or removing rows with missing values. Asterisk encoding categorical variables, asterisk converting categorical variables into numerical representations, example 1 hot encoding. Asterisk hyperparameter tuning, asterisk the performance of a neural network depends heavily on the choice of hyperparameters, such as asterisk learning rate, asterisk controls the step size during optimization. Asterisk batch size, asterisk the number of training examples used in each iteration. Asterisk number of layers and neurons, asterisk the architecture of the network. Asterisk regularization parameters, asterisk the strength of regularization techniques. Asterisk use techniques like grid search, random search, or Bayesian optimization to find the best hyperparameter values. Tools like keras tuner are very helpful. Asterisk overfitting and underfitting, asterisk. Asterisk overfitting, asterisk the network learns the training data too well and performs poorly on unseen data. Use regularization techniques to prevent overfitting. Asterisk underfitting, asterisk the network is not complex enough to learn the underlying patterns in the data. Increase the complexity of the network or train for longer. Asterisk vanishing/exploding gradients, asterisk. Asterisk these problems can occur in deep neural networks, making it difficult to train the network. Asterisk use techniques like ReLU activation, batch normalization, and gradient clipping to mitigate these problems. Asterisk initialization, asterisk the initial values of the weights can significantly impact the training process. Use proper initialization techniques, example Xavier/Gloro initialization, He initialization. Asterisk hardware, asterisk training large neural networks can be computationally expensive. Consider using a GPU or cloud-based resources to accelerate the training process. Google Colab offers free GPU resources. 7. Conclusion. Neural networks are a powerful tool for solving a wide range of machine learning problems. This tutorial has provided a comprehensive overview of the fundamental concepts, architectures, training algorithms, and practical code examples. Remember that building and training successful neural networks requires experimentation, careful data preparation, and a thorough understanding of the underlying concepts. Good luck and have fun exploring the world of neural networks.